continuing from where we left off, we showed that if f is continuous and one-to-one on an interval, then f is either increasing or decreasing on that interval. An important consequence of that corollary is that if f is continuous, if f continuous and 1 1 and 1 1 on an interval AB, A comma B, where you're allowed to have negative infinity to infinity, could be negative infinity to infinity, then FAB, which is the entire image of this interval, is also an open interval, which could also be negative infinity to infinity. Okay, and I am not going to prove it completely. I'm going to give you the sketch of a proof. Okay, so look at f of AB. Okay, take C in AB. Okay, first of all, f is continuous and one-to-one on the interval AB means either it is increasing or decreasing. So assume f increasing on A to B. It doesn't matter if it's decreasing, the proof will be exactly reversed. Okay, so let us assume that it is increasing. If so now you have two choices. One is that f is unbounded. So 1, f takes arbitrarily large values, as it goes to B, in which case the image is going to be up to infinity, right? So you'll get the infinity part. In the second case, f is bounded above. F is bounded above. Okay. Well, in that case, A is equal to f of x, such that C is smaller than or equal to x smaller than B, has a least upper bound. So least upper bound, which I'm going to call alpha, as a LUB alpha. Okay. Then for any alpha for any f of c, for any y such that f of c is smaller than y smaller than alpha, we can have that by intermediate value theorem, by intermediate value theorem, what was I saying? Oh, by intermediate value theorem, f of x takes, okay, I think I skipped a step, sorry. So for any f takes a value, f takes some value f of x greater than y, right? This is because if f did not take any value, then y would be the least upper bound, right? So there is some value more than y which is taken, then by IVT on C2x, there is some f takes the value f takes the value y for some x or for some point, right? So the value y is taken, right? Notice that f cannot actually take the value exactly alpha. F cannot take value alpha, because if it did, then otherwise alpha. Suppose it did. Suppose f of t is equal to alpha for t smaller than t in AB. Then there exists x1 in a comma b such that x1 is greater than t, and therefore f of x1 is greater than t, which is greater than f of t, which is equal to alpha, contradicting alpha is LUP, right? And so therefore A is bounded above by alpha, where A cannot take alpha. Similarly, image of f is bounded below by some beta. Therefore f of a comma b is an open interval. It could be that in some it is negative infinity to, let's say, 7 open or something, right? Only one of the sides is going to infinity, but in either case it is an open interval. Okay, then theorem 3. If f is continuous and 1 to 1, continuous and 1 1 on an interval, then f inverse is also continuous. Then f inverse is also continuous. Proof? I'm going to give you the easy proof first. Easy proof. The graph of f inverse is continuous, since it is the graph of f, since the graph of f is continuous, right? And f inverse is just flipped around xy. And graph of f inverse is obtained from it by reflecting around y is equal to x. Okay, but this is not a good enough proof for us. We might want to be more formal. We want a good formal proof because we are doing this course in a good formal way. And so we are going to do a more rigorous proof using epsilon delta. Formal proof. Formal proof. Once again, we are going to assume that f is increasing. The proof will work similarly for f decreasing. And we are going to assume that our interval is open. It doesn't matter if it's closed. It's just you have to do some more things. You can just extend it to an open interval. Okay. So because you can, if you have a continuous function which works on a closed interval, you can more or less always extend it slightly to some open interval in a meaningful way. Assume f increasing and interval AB open. Interval A comma B. Okay, again, you can have infinity, which is fine. So in that case, we want to show, or maybe I shouldn't have chosen AB. Interval is open. Then we want to show that given any point, therefore want to show limit x goes to, let's say, b of f inverse of x is equal to f inverse of b. So as b, we are saying it goes to a, whatever we want to say, f inverse of b is equal to a, and want to show f inverse of limit of f inverse goes to this thing, right? So is equal to a. Okay. So because f is continuous, since f is continuous, I have that for every epsilon. Okay, let me say this. This is equivalent to saying equivalently for every epsilon greater than 0, there exists a delta greater than 0 such that if f of a minus delta smaller than x smaller than f of a plus delta, which is to say the distance between f of a and x is less than delta, then a minus epsilon is smaller than f inverse of x is smaller than a plus epsilon. And the reason I'm writing it like this is rather than in the absolute value sense is because I am going to use this expanded form. Okay, so here's how we are going to do. Well, we know that a minus delta, since a minus epsilon is smaller than a plus epsilon, therefore, and f is increasing, f of a minus epsilon is smaller than f of a, which is equal to b, is smaller than f of a plus epsilon, right? Oops. Then take delta is equal to minimum of absolute value of f of a minus f of a minus epsilon minus f of a, comma f of a plus epsilon minus f of a. Okay, I'm going to take delta to be the minimum of this. Okay, then what is happening? Therefore, f of a minus epsilon is smaller than or equal to f of a minus delta, and f of a plus epsilon is smaller than or equal to f of a plus delta, and this will be the other way around. F of a plus delta is smaller than or equal to f of a minus epsilon, a plus epsilon, right? Because delta is the minimum of these two. If I take it in here, I'm going to hit at most one of these two, whichever is larger, whichever is smaller, right? Therefore, if I take this as my delta, I have that since x lies between these two, therefore f of a minus delta is smaller than x, smaller than f of a plus delta. F of a plus delta implies f of a minus epsilon is smaller than x, smaller than f of a plus epsilon, right? And therefore, because f inverse is also increasing, since f is increasing, f inverse is also going to be increasing. F inverse of f of a minus epsilon is smaller than f inverse of x. Oops. Is smaller than f inverse of f of a plus epsilon, and therefore a minus epsilon is smaller than f inverse of x is smaller than a plus epsilon, which is to say, which is exactly what we wanted. Therefore, f inverse of x minus a is smaller than epsilon, right? This condition was basically equivalent to, x minus f of a smaller than delta. So I have shown that x minus f of a smaller than delta implies that f inverse x minus a is smaller than epsilon, and therefore my f is continuous. F inverse is continuous. Okay, great. Then theorem 4. Theorem 4. If f is continuous and 1-to-1, f is continuous and 1-1, defined on interval, defined on an interval, and suppose f prime of f inverse of f inverse of a is equal to 0, then f inverse is not differentiable at a. F inverse is not differentiable at a. Proof. This one's really relatively simple. Suppose f was differentiable. Suppose f inverse was differentiable. Suppose f inverse differentiable at a. Well, we have that f of f inverse of x is equal to x, right? Therefore, f by chain rule at a, prime of f inverse at A multiplied by f inverse prime at A is equal to 1, right? But f prime of f inverse of A is equal to 0. Therefore, 0 times f inverse prime at A is equal to 0. Okay, and that's not possible. Contradiction. Therefore, f inverse is not differentiable at A. Relatively simple. An important point here is that we can only use chain rule if f inverse is differentiable at A. We cannot use the chain rule otherwise. Okay? And so, next theorem. Oops. Theorem 5. Let f be a continuous one-to-one function, f continuous and 1, 1 on an interval, 1, 1 on an interval, and f is differentiable at f inverse b. And suppose f differentiable at f inverse b with derivative f prime of f inverse of b not equal to 0. Then f is differentiable at b and f inverse prime at b is equal to 1 over f prime of f inverse of b. Okay, proof. Once again, it's very tempting to say, oh, look at this right here, right? This step right here. Instead of A, if I write B, then it's exactly what I have. F inverse prime at B is equal to 1 over f prime of f inverse of B. And life is great. There's a small problem. If this thing, chain rule, works only if f inverse is differentiable at, in our case, B. As of now, we have no idea if f inverse is differentiable at B, right? My theorem says then f is differentiable, f inverse is differentiable at B. This should have been f inverse. F inverse is differentiable at B, but I need to prove that first. So let us do that. Let B is equal to f of A. Then I have that limit h tends to 0, f inverse of B plus h minus f inverse of B all over h, which is what the derivative at B is, right? Which is what I want to show exists. This is going to be equal to limit h goes to 0, f inverse of B plus h minus a over h. So that we are writing like this just for convenience. Because f is continuous, let f inverse of B plus h is equal to a plus k as f is continuous. There's some number. F inverse is going to exist. It's a one-to-one function. B plus h is in the domain, so we are going to have some element which is its inverse. I'm going to write it as a plus k, whatever the value of k is, right? So I am writing it like this. Therefore, limit h tends to 0, f inverse of b plus h minus a over h is equal to f inverse of b plus h is equal to a plus k. So a plus k minus a over h is equal to, over, let me be slightly sneaky. On the top, I have a plus k, but on the bottom, I have f of a plus k minus f of a. Oh, limit h goes to 0. Right? Which is equal to limit h tends to 0 k over f of a plus k minus f of a. Now, since f is continuous, since f and f inverse are continuous, since f and f inverse are continuous, limit h approaches 0, limit continuous, what did I want to say? As h approaches 0, k approaches 0, right? Because what is k? K is f inverse of b plus h minus f inverse of f inverse of b, right? As k is equal to f inverse of b plus h minus f inverse of b, right? Limit of f inverse of b plus h, f inverse limit f inverse of b plus h is f inverse of b. They are going to go to the same term. So as h goes to 0, k goes to 0. Therefore, limit h goes to 0, f inverse of b plus h minus f inverse of b over h is equal to limit k goes to 0. Let me rewrite this term as 1 over f of a plus k minus f of a over k, which by definition is equal to limit is by definition equal to 1 over f prime at a. And what is a? A is exactly f inverse of b, so therefore this is 1 over f of f prime of f inverse of b as required. Okay, and hence we have the proof, and that is the final result of this chapter. So that concludes chapter. Let me do an example, actually. Let's do a couple examples since we have time in this one. So that's the final theorem, that's the final result. Exercise. A. Prove that there is a differentiable function f such that f of x to the 5 plus f of x plus x is equal to 0. Part B, find f prime in terms of f, and part C, find f prime by another way by simply differentiating. Okay, so how do we do this? Well, answer. So for the first part, what we are going to do is show that f can be written as, let's say, we'll find some inverse function that we can write. So let f of x is equal to y. Okay. Then f inverse of y is equal to x, right? And therefore I get, in terms of y, this function becomes y to the 5 plus y is equal to x, y plus x is equal to 0. Therefore, y to 5 plus y plus f inverse of y is equal to 0. Therefore, f inverse of y is equal to negative y minus y to the 5. Right? Well, great. Y is differentiable. Y is differentiable. Well, sorry. F inverse y defined this way is 1, 1 and differentiable. Actually, let me do this slightly better. So therefore f prime of, f inverse prime of y is equal to negative 1 minus 5y to the 4th is always smaller than 0, right? Therefore, f inverse of y is decreasing for every y. And because it's a polynomial, it is continuous. Therefore, f inverse y is continuous, 1, 1, and differentiable everywhere. Therefore, f inverse of y, f inverse is continuous, 1, 1, and differentiable. Because the derivative is never 0, the derivative of f inverse is also is well defined, and therefore f inverse is continuous and differentiable, right? Therefore, but f inverse is just f, therefore f is continuous, 1, 1, and differentiable everywhere. Okay. Part B, I need to find f prime of x is equal to 1 over f inverse prime at f of x, right? And f inverse prime is equal to 1 over f inverse prime at y, is equal to 1 over f inverse prime I know is negative 1 minus 5y to the fourth. 5y to the fourth. Right? And that is equal to did I make a mistake somewhere? Yeah, is equal to 1 over 1 minus 5. Well, y is just f of x, so f of x to the fourth. That is fine. Great. Part C, I want to find the derivative some other way. This method is called implicit differentiation by implicit differentiation. Well, what is the derivative? Now that I know that f of x is differentiable and continuous and all nice things in the world, sugar, spice, everything nice, I get, by chain rule, this is taking the derivative d over dx of all of this is equal to, is equal to d over dx of 0. Therefore, 5 times f of x to the power fourth times, by chain rule, f prime of x plus f prime of x plus 1 is equal to 0. Therefore, 5 times f of x to the power 4 plus 1 into f prime of x is equal to negative 1, and therefore f prime of x is equal to negative 1 over 1 plus 5 f of x to the power 4, which is exactly the same as what we had before. And that concludes our example. I'll stop here. We might look at more examples before final exam, but this is for this chapter.